Okay, so today we're going to do one more CH kind of substitution reaction with the radical mechanism. It behaves a little bit differently, but it's complementary to what we've seen before. And then we're going to transition into the other type of substitution mechanism that proceeds through ionic, or two electrons moving, and that's called SN2. So we'll focus probably on SN2 this week, and then do the other mechanism of that, which is SN1. And as we go through this, we'll explain what that nomenclature means, what is it telling us about the mechanism and the kinetics that are occurring, but ultimately how it allows us to transform functional groups and make more complex molecules. So the first reaction that we're starting today it's still a radical mechanism. It behaves a little bit differently than just a CH substitution that we've seen before. So there's a word on here that's probably new called regiochemical, and that relates to the addition of two elements or substituents to an alkene. And so when we have alkenes that are not symmetric about the pi bond, we can add things in two different ways. So we're going to talk about what factors influence that. And the species that we're going to use is HBr. So when you look at HBr, chemically you think that's an acid, but under the conditions that we're using, we're still generating radical intermediates. So there's this other stuff in there that influences the reactivity of the HBr. So if we look at the reaction overall, we have this alkene. It has one substituent. It's mono-substituted. So there's our alkene. There's our one substituent. So of the two sp2 hybridized carbons of the alkene, they're both different. And that's where this word regiochemical comes into play. So we're treating the alkene with HBr in the presence of this chemical called tert-butyl peroxide. In general, the peroxide functional group is an oxygen-oxygen sigma bond. And then you can have whatever bonded to that central two oxygens there. So that's a peroxide. And I think I mentioned this before. When you have two heteroatoms connected by a sigma bond, that's a pretty weak bond. So that bond will be homolytically cleaved. That generates radicals. And so that's why overall this is a radical mechanism. But if you look at the HBr, so there's two different elements, H and Br. In the products, we're adding H and Br across that double bond. So that's where the word addition comes into. So addition is different from substitution when we're talking about mechanisms. So of the two possible products, they're related in the sense that they're constitutional isomers. But you can see that the H and the Br have added to different carbons of the alkene. And so that's what the word regio means. Of the starting alkene, what carbon is getting which atom of that reagent? So if we classify the major versus minor in terms of the halogen. The major product would be called a primary bromide, and the minor or not formed would be secondary. So if we further recall back to the CH substitutions that we were learning, the general trend is that the more substituted halogen product is going to be formed. So overall, what these conditions are complementary to the reactions that we learned in the first couple lectures of this module. So to draw that out briefly, if we were to take propane and treat it with bromine and light, propane has two unique sets of hydrogen, primary and secondary. The secondary CH bonds are weaker, and then paired with bromine, we know that there's going to be selectivity to substitute at the secondary position. So the conditions we first learned give you the more substituted halogen. Now these conditions give you the lesser substituted as the major product. And that all relates to the radical mechanism. Notice the difference in the halogen source and then the presence of this peroxide. So over the next couple slides, we'll talk a little bit about how this kicks off in terms of the thermodynamics, the radicals that are formed, and then what they do to that alkene. That kind of switches this major versus minor. So again, if we refer back to the bond association energy table, we can look up the values of HBr and Br2. So the question is, since HBr has a larger bond association energy, it's plus 366 versus bromine, which is plus 193. Why would we even use that as a reagent if it's easier to cleave this bond to begin with? And that relates to using the peroxide in the reaction to change the product distribution. So this particular peroxide is tert-butyl, so ditert-butyl peroxide. That bond association energy is plus 157, so it's even lower than bromine to begin with. And that means when it cleaves, we form two of these tert-butoxy radicals. So remember, radicals are reactive intermediates. They're high energy. They want to do something so that they become neutral. So what this thing will do in the next step is react with the HBr to abstract a proton. And so we can move electrons like that to form an OH bond. Now we have a neutral alcohol and then a bromine radical. So overall, this sort of initiation and then start of a propagation is exothermic, so that's favorable. Now the bromine radical, since we're not using just a standard alkane. We have an alkene. It's going to react with the pi bond of the alkene. And so there's propene, and I've labeled those carbons A and B. So at this point, the bromine has a choice. Can it add to carbon A or to carbon B? And so you'll notice that the arrow splits here, and we want to draw the reactive intermediates that form from both and then compare them. So maybe what I'll do, let's use some different colors here. So the red arrows are going to show the bromine radical adding to carbon A. So we need to supply that one electron. Then one electron of that pi bond comes over. That forms the carbon A to bromine sigma bond. And then that remaining electron of the pi bond ends up on carbon B. So we just formed this sigma bond, and that results in a radical at that carbon. So if we classify that radical, we can see that it's secondary. So we'll do the same thing, but now we'll add the bromine to carbon B. Don't want to do that. I want to do it so that, and then this arrow coming there. So this is showing carbon B then gets the bromine, and then carbon A gets the radical. So if we classify that radical, it's primary. So at this point, since we drew out both scenarios, essentially what we're comparing is what is the ease to form those radicals. And that gets back to the table of bond dissociation energies. So tertiary is greater than secondary is greater than primary, meaning that path A is going to be preferred because that radical is more stable. So now we have a carbon radical that needs to be quenched, and it will get its hydrogen from the HBr. So that radical abstracts a proton. We homolytically cleave the HBr bond. We end up with our product. That's the lesser substituted bromide, and then a bromine radical that propagates the mechanism. So when you're thinking about this split that happens, remember it's climbing that energy mountain. So the thermodynamics dictate that you go over the smallest hill to expend the least amount of energy. So overall, this is a complementary method to the normal CH substitution. So the important thing is, no matter what your alkene you're starting with, you do have to go through this process of adding the halogen radical to both carbons and then evaluating the stability of the resultant carbon radical. So the more stable radical is the one that's selected to move on to form the major product. So to reiterate what this word regiochemical means, and we're going to revisit this later in Module 5. When you have an alkene with this type of reagent, you can add the H to A, the bromine to B, or you can flip it around. So those are the choices. That's what regiochemistry means. The major product is dependent upon the reagents that are in there and the mechanism that it's proceeding by. So under this radical addition, you get this lesser substituted halogen because that intermediate is a secondary radical which is more stable. And so notice this bromine dot radical. That's the propagating radical that can go back here, react with the second equivalent of your alkene. And so this will continue on till all of the alkene is consumed. So keep this highlighted trend in mind when you're evaluating these two different possibilities about major versus minor. Any questions? So of the two proton NMRs shown, which one corresponds to the major product? I think I could read some lips. A is the correct response. So what are we looking for? So the major product is going to have three unique sets of hydrogen, and we can see it 1, 2, 3. The minor product is going to have 2, so 1 and 2. And at that point, we're able to answer the question. We don't really have to get into number of neighbors, multiplicity, or coupling at this point, just because the unique sets are sufficiently different. So let's see if this makes sense. We have an alkene, HBr, a peroxide, and we want to determine what is the major product. Notice now there's the carbon-carbon pi bond, so there's the alkene. We have 1, 2, 3 substituents, so this is tri-substituted. You still have to go through the process of adding that bromine radical to each of the sp2 hybridized carbons to evaluate which one of the resultant carbon radicals is the most stable. So let me want to color these a little bit different. So those are the 2 carbons of the alkene. The substituents here are going to be in red. So the reason that matters is because it helps you classify the radicals that are formed. So let me draw out the 2 carbon radical intermediates, and we'll see if we can figure out the name of the product. So that bromine, it can add to the blue carbon, which will put a radical on the green carbon. Or it can add to the green and put a radical on the blue carbon. So in the first case, let's take the bromine. We're going to form the bond to this blue carbon. And so that puts the radical on the green one. In the second case, we just do the opposite. So now of these 2, we have to classify the radical substitution. So this one with the green has 1, 2, 3, so that's a tertiary radical. The one in blue has 1, 2. So on the stability trend, the tertiary one is going to be preferentially formed. So that's going to lead to the major product. And so what name do you think corresponds to that major product? So choice B, 1-bromo 2-methyl cyclopentane. So remember that a radical carbon is sp2 hybridized. The single electron is residing in the p orbital. So when we're standing on that carbon, what we're doing is counting how many other carbons are bonded to it. So we have 1, 2, and 3. So down here on the blue one, we just have 1 and 2. The third thing is the hydrogen, which isn't drawn. Yeah.
Why do you choose the 3' over the 2'? Is it because the 3' is more stable?
Yeah, the tertiary radical is going to be lower in energy, so more stable than the secondary. And so that's the one that's going to go on to react with HBr to get quenched to form the product. So overall, where that alkene was, we've added the elements of HBr across that alkene. And what that does in terms of classifying the product, this is now a secondary bromide. So of the two possibilities here, secondary versus tertiary, in relation to the bromine now, the lesser substituted one is the major product. So as you go through, the mechanistic or radical intermediates, you're classifying things one way, but then the products, you're classifying them a different way. And as I mentioned in the run-up to the final exam, you've seen HBr in terms of it being an acid. We'll see it again later on this semester. But when it's in the presence of this peroxide, it's behaving a little bit differently due to the nature of the mechanism. So when you're diagnosing reaction conditions, you not only have to know their reactivity, but how is everything else affecting it? And so how does this act upon that functional group? So under like this brew of reagents, the peroxide is what is forcing that to be a radical. And then due to the kind of thermodynamics of the pi bond and the other stuff in there, this does add to form the carbon radicals. But later on, again, this semester as a preview, you're going to see HBr reacting with an alkene, and it doesn't have the peroxide in there. So essentially, what it does at that point is flip the product distribution around because the mechanism is different. So you have to know whether it's going through a radical mechanism, so 1 electron, or ionic, which is 2 electrons. So how many stereogenic centers does the product have? So it has 2. And that leads to 4 possible stereoisomers. So a couple lectures ago, I posed this problem of starting with methyl cyclopentane with chlorine and light, and then asked how many monochlorinated products there could be. The first answer that was fired off was 3. Then someone said more than 3. So when I went through that, I got 10. And it relates back to the intent of this question. That substituent on the ring, when you start substituting other places, that will become a stereocenter. So if you generate a molecule with 2 stereocenters, then you have this 2 to the n, and that's how this number gets so big. So I guess the thing to be aware of, in either of these problems, even though that is not a stereocenter to begin with, the fact that the mechanism by which it proceeds can generate a stereocenter. Questions? So of the 2 structures shown, what is their relationship? So the answer is C. They're diastereomers. So they're drawn relatively the same, that you can sort of map the cyclohexanes on one another. And when you do that, you'll see that this methyl group, that stereocenter stays the same. But then the bromine switches. And since they're not exact opposites of one another, they can't be enantiomers. So one stays the same, the other changes, they have to be diastereomers. So again, you can do those type of problems 2 ways, depending upon how it's presented to you, either looking at the R and S nomenclature, or given the structures, make sure that you can sort of visualize how they map onto each other and if those stereocenters are staying the same or switching. Any questions? 'Cause I think that's the last slide on the radical stuff. So those prior mechanisms, again, proceeded through a single electron or radical mechanism. We're now going to start with ionic mechanisms. So ionic mechanisms proceed through two electrons moving. And the arrows that we're going to use have that double-headed arrow there. So the radical ones use kind of the fish hook or one-sided arrow. So when you see that, that's the movement of two electrons. And as we proceed through this module and then the next module, there's two types of mechanisms, so substitution and elimination. This is called nucleophilic substitution because the nucleophile is supplying two electrons to attack a substrate that has a leaving group. That's a little bit more intuitive in terms of what we learned for assigning electronegativity, delta plus, delta minus, and what we're normally used to thinking about who owns the electrons in a bond, in polar covalent bonds. So substitution is exactly that. Some group is getting substituted for another. Elimination is Module 5 stuff, which we'll talk about, but elimination means we're forming a pi bond. So right now we're focused on substitution. What we've seen so far is we can take an alkane with a CH bond and then substitute it for a halogen X. Now we're going to generalize this. Once we have this alkyl halide, we want to substitute that X for any other functional group we've learned. So an example of this is shown in the center here. We have bromomethane. So if we put in the lone pairs there, bromine has 3, so we can say that bromine's delta minus and the carbon's delta plus. And we're going to react that with sodium hydroxide, where that oxygen is negatively charged. If you look at the reaction overall, the bromine has been substituted for the hydroxide, so we've made an alcohol. So that is the substitution part of it. The nomenclature part this anion, using just the general term, the anion is supplying electrons to form a new bond. That's called a nucleophile. The partner over here that has this delta plus carbon, that's called an electrophile. If we broaden that to like the general acid-base definition, a nucleophile is a Lewis base, an electrophile is a Lewis acid. That supplies electrons, that accepts them. But we use these terms more for describing the substitution mechanism. The electrophile always has the group that's going to leave or is substituted. So that's called the leaving group. So the nucleophile attacks the electrophile. This group leaves. We have our product where a substitution has happened. And then we get this inorganic stuff that you can think of as like spectator ions. So just so that we're clear, when we use this term acid-base reaction, that's typically the movement of a hydrogen from one substrate to the next. So that's a class of reactions. As we expand the library of reactions that we're discussing, we're going to use these terms nucleophile and electrophile because they do not involve hydrogen. And they're more generally applicable to most of the reactions we'll learn. The specific mechanism that we're learning here first is called SN2, which stands for substitution, nucleophilic. The 2 is bimolecular. That relates to the rate. How fast does the reaction proceed? The 2 is dependent upon the concentration of both the nucleophile and the electrophile. So for this reaction to go, that nucleophile has to collide into the electrophile. Both of them need to be present as the mechanism proceeds through time. So that's where the 2 comes from. So as I just highlighted in green here, the nucleophile supplies electrons that attack the electrophilic carbon. You then cleave the carbon leaving group bond. So the reason the arrow again points that way is we initially assigned that bromine as delta minus. So because it's delta minus, it can accept those 2 electrons and be happy about it. From where we started, bromine has been substituted by OH, or the nucleophile. So this isn't the best representation due to the limitation of my drawing skills and ability to put time into making stuff fancy. This arrow has to attack 180 degrees opposite to that bond. And so over the next couple slides, we'll explain why that is. So the trajectory has to be exactly behind the carbon leaving group bond. So as I've highlighted up here, we have a carbon and a bromine. So that's our normal covalent bond we're used to seeing. So it's a sigma bond, and that's the notation. Sigma carbon bromine. when we make that bond, we have an sp3 hybridized carbon that's bonded to a bromine. Each of those elements is supplying an orbital. So that's 2. Then we have this polar covalent bond, which corresponds to 1. So there's this other thing that forms when those 2 orbitals combine, and that's called the sigma star or anti-bonding orbital. The directionality of this bond, so the electron density is in there, it's more towards bromine due to electronegativity. The anti-bonding orbital is 180 degrees, sort of the opposite direction. So we have sigma and sigma star to conserve the number of orbitals involved from the start. And what does that mean? We have 2 electrons. They have to go somewhere to form a new bond. And where they're going is into this empty sigma star orbital to form an O carbon bond. The existing sigma bond with the electrons between carbon and bromine, those go on to the bromine. So it becomes negative. So notice kind of the formal charge dance around here. The nucleophile has a negative charge, the O minus. The leaving group ends up with a minus charge. And the metal, sodium, is just a spectator that is balancing off with its positive charge. So to recap that, the sigma bond has 2 electrons, the sigma star has none. It has to exist to conserve orbitals, but again, conceptually, it helps explain where these electrons of the nucleophile are actually going. So the trajectory of 180 degrees arises from the geometry of this math, basically. That sigma star is 180 degrees from the existing polar covalent bond. That's mechanistically the overview of the arrow pushing. How does this get more complicated? We're going to look at the strength of the nucleophile, the ability of the leaving group to leave and support the negative charge. And then what you'll notice is we started with carbon, which is a methane derivative, but what about when we start substituting these H's for other things? How does that affect primarily the rate of the reaction? How fast will it go? Will it go at all? The other thing which I've kind of drawn suggestively, getting a little busy with the colors here, but so those 3 hydrogens I've kind of highlighted with a triangle. So notice in the starting material side, that triangle is sort of towards the left. Now it's towards the right. The implication is that if that carbon is a stereocenter, so it has 4 different substituents, whatever those 3 things are, from the starting material to the product, there is an inversion. And that also deals with how the mechanism proceeds of electrons moving from the nucleophile, forming a new bond, breaking an existing bond. So we're going to be haunted by stereochemistry, R and S, and all of that stuff as we move forward. Any questions? So these next couple slides will focus on this, the 2 part of it, the bimolecular. So I'm just going to use those abbreviations, nucleophile, electrophile. When we talk about rate, kind of the easiest thing to think about is time. And one way to generalize rate to make it real to you is just traffic. What's the easiest time to escape the Hattiesburg campus? It's definitely not 7:30 a.m. on a Tuesday or 5 p.m. any day. That's a slow rate, right? There's a lot of people leaving or coming into campus. So you can think of rate sort of as congestion in a sense. So there are factors that will affect the rate, structural factors. But overall, you need both the nucleophile and the electrophile to be present for the reaction to proceed. And that's reflected in this rate equation. So whatever those 2 species are, the square brackets use the units of molarity. And then you have some rate constant K that needs to be measured for each unique reaction. So on the reaction coordinate from time 0, then everything gets into the flask, time starts proceeding. We can graph the energy requirements as time moves along. And so the rate is affected by this energy of activation. And every sort of mechanistic type has general patterns to it. But the energy of activation is basically the highest point on that curve that has to be overcome for the rest of the mechanism to proceed. For an SN2 reaction, that corresponds to a transition state, which again is a real thing, but it only exists for a very small amount of time. And here's the coordinate. So we have time proceeding from left to right on the x-axis. Then on the y-axis, we have this relative energy. Our starting material well. We have our nucleophile, our electrophile. So you need to think of these things, even though they're static images, as they have to get close in proximity to react. So that means there's distance. And as they get closer, you have bonds forming and breaking. It doesn't happen like on a quantum scale where it's either on or off. There's these distances that change. It never goes from like not bonded to bonded. And so as you move up this hill, notice it's increasing energy to this highest point. The highest point is the transition state as depicted with this square bracket and then that dagger. For our SN2 mechanism, we have the oxygen-carbon bond partially forming, and then the carbon-bromine bond partially breaking. So overall, that might look weird, or you'd throw up your hand and say, well, that's 5 things. 1, 2, 3, 4, 5. And you said that according to Lewis dot structures, carbon can't form 5 things. So there's this rehybridization that happens in the transition state where that carbon is kind of sp2. Then you have this p orbital that allows for bonds to form and break, again, only for a very short amount of time. So as it proceeds, that ball then rolls down the hill and you get your products. And to maybe one step up to make some movement. So if this is so we'll just consider this carbon as methane. So these are H's. This thing is the leaving group. And then this ball here is the nucleophile. It has some electrons associated with it. This is the sigma bond of the carbon leaving group, those 2 electrons. The anti-bonding orbital is right here. It's sort of in this area where these hydrogens are. You can't see it, you have to imagine it. But the nucleophile has to approach 180 degrees opposite to that, because that's where that anti-bonding orbital is. It can't do this way, it's not some other trajectory that's happening. So it's got to come this way, like they're far apart, nothing's happening, but now it's closing distance. And when it does that, it's eventually going to slam into there and that's going to leave. But at the highest point, now we have this sort of central carbon, the 3 hydrogens. The transition state it will look like that, sort of this 5-coordinate thing, where these 3 substituents of carbon that are still remaining, they have to be in a plane. And so this is kind of like your p orbital. This bond is forming, this bond is breaking, and then that's going to leave. So I probably should have brought another model, but I'll do some cheap magic. So these 3 hydrogens, this is coming this way, this leaves. So notice they're on this side. Here's the magic trick loop. Now they're on this side. Because when this is planar, they have to invert to the other side. And that will have implications if the existing carbon is a stereocenter. whether that matters or not for an inversion. The other thing that I want to point out on here is, notice these terms changed a little bit. So the blue arrow, which requires energy, is called endergonic. The red arrow, which is releasing, is called exergonic. And the reason we're not using endothermic or exothermic, because that term now is changed to G, which stands for Gibbs, and it includes all the other variables that can quantify this system. So the delta G means the Gibbs free energy change. And when you look at, the furthest right side of the equation, this is what you're used to seeing, that H, the enthalpy. But now it's including temperature and this S thing, which is entropy. And if you understand what the word entropy is, please explain it to me, because I do not. It's very hard to conceptualize what that means. The kind of broad term people use is disorder or chaos, but really, how do you think about that? One way to rationalize it in terms of this equation is that the universe prefers to proceed towards chaos. And if you think of your dorm room or your apartment room and you've cleaned it, everything's orderly, how does it look 5 days later? Is it still the same, or are there clothes and Chick-fil-A bags all over the floor? Things get more chaotic over time. And that's a favorable component overall to this, is if you increase the entropy. But your delta H is your bond dissociation energies, and then your time here. Overall, that stuff accounts for a more standard way of reporting these energies. And so we slightly just changed these terms because we've normalized it according to these other variables. So other than just showing you that to say I did and check the box, I don't really focus too much about plugging stuff into there. So really what we're going to do is look at the structural features of these things that really affect the rate, because we want a reaction to be productive. So how do we maximize these features that's going to make a reaction synthetically useful? Or stated another way, what's going to kill a reaction? Like if we're trying to put stuff into a flask and nothing happens, what was on that molecule that prevented this mechanism from occurring? The take-home message for this slide for an SN2 reaction. When you look at the carbon bearing the leaving group, the rate is dependent upon this, this trend here. Your typical methyl group will always react the fastest. And if we consider, this would be methyl. So all of these things are hydrogen. But if you take one of these off, and now it's some other group, now it's primary. Take another one off, it's secondary, the third one. So different groups now. So this actually shows this carbon now has 1, 2, 3 methyl groups. So this would be a tertiary carbon. And according to the trend, these are not reactive. And so we'll think about why that is, why that's observed experimentally. So you look at your starting material with the leaving group, you classify it. If it's tertiary, it's not going to undergo an SN2 reaction. So the table here shows methyl, primary, secondary, tertiary of the carbon bearing the leaving group. So I'm calling that an alpha carbon. So with the methyl, everything's H. Then the primary, we've just done a substitution of H for a methyl, but it can be whatever. Secondary, we've done 2 of them, and then tertiary, all 3 are substituted. The reason that we observe the rate trend if you put your eye like right behind that carbon that's bearing the leaving group, this blue dot is meant to represent the anti-bonding orbital that has to be attacked. And then this line here, or this column here, is kind of showing you the surface area of that carbon that's available, conceptually meaning the anti-bonding orbital that's free. So we have 3 hydrogens. So you can see a lot of that gray area. But as we start substituting for other carbons, notice that surface area decreases, and by the time you get to tertiary, you can barely see it. So overall, we benchmark the secondary as 1 in terms of rate, meaning that a primary will react 50 times faster and a methyl 1,000 times. And the tertiaries are essentially a trace because this is a ball and stick model. That's called space filling. That little blip there, like in the middle, you can barely see it now. But that's where the anti-bonding orbital is. The electrons in this nucleophile will have a hard time getting there. That's called sterics. All of this stuff is blocking that anti-bonding orbital. So remember, it doesn't extend out to infinity where it can be this far away and still bond. It has to be pretty close, but it's going to bang into these groups whatever they are. And so the tertiary substrates, as you see, the rate is very slow if they do it at all. And again, that's the trajectory of this mechanism. There's a special case where we have a primary. So the carbon bearing the leaving group is primary. but now this beta carbon is fully substituted. So because that beta carbon is tertiary, it's given this name neopentyl. It has the same effect where it's inhibiting access to that anti-bonding orbital. So even though it meets the sort of rate requirement for classifying the carbon as primary, the hindrance of that beta carbon essentially shuts down any substitution because the anti-bonding orbital is blocked. So the space filling is probably the more accurate depiction of what a molecule looks like, but they're a lot harder to just interpret. These sort of drawings are easier to interpret, or the ball and stick, like with your model kits. So each has its plus and minuses. The ball and stick, you might fool yourself into thinking, yeah, it could still happen, but the space filling is more accurate in terms of kind of the volume that shows it's not accessible. So we'll end today on this slide where really what we've focused on is the electrophile. So you want to classify the carbon bearing the leaving group. Is it methyl, primary, or secondary? That will tell you, okay, this can happen. If it's tertiary, it won't. Where we're going with this, we're going to look at what makes a good leaving group, what are the nucleophiles, and then how do things like the solvent and temperature play a role in terms of the rate at which it occurs. And so again, the thing to keep in mind, once you form that substituted product, how do you identify that functional groups using IR, proton, and carbon NMR?